So in section 7.8, we're going to go over improper integrals. Now, what is an improper integral? Well, an improper integral is something where one of the limits of your interval is something like infinity or negative infinity. That's one possibility, or you could have both. And then there's another possibility as well. That other possibility is that at one of the endpoints of the integral, the integrand is undefined. For instance, sine of 0 is 0. Well, you can't divide by 0. We know that's a problem. Likewise over here, at x equals 5, the denominator is 0, meaning the quotient is undefined. But there's still ways you can try and figure out an answer for these things. So we're going to work with these, try and figure out, when an interval has an answer. And if your integral has an answer, then it's said to converge. If it doesn't have an answer, then it's said to diverge. So those are going to be our two extremes here in working with this kind of stuff. So let me get started with kind of the more friendly of the crowd here, which would be this one right here. So for example 1, we'll take a look at the integral from 2 to infinity of e to the negative 5p dp. Now let's try and understand kind of visually what's going on when we're looking at this type of an integral. And I'm going to go back to my favorite friend, Desmos, for that. And yeah, see, I do have this one sketched out. So remember that the definite integral has an interpretation with respect to an area. And what we're trying to find in this case is the area beneath this curve and above the x-axis starting at 1 to infinity. Is it 1 to infinity? No, 2 to infinity. Oh, so I should probably bump this up. 2 to infinity. There we go. Let's make that a 2. Wow, let's see, we've gone. So what's going on here is that this curve is really, really close to the x-axis. Man, I can't even hardly see it. Look at how much I have to zoom in before you start to even a little sliver of it. And so I said we're trying to find out if the integral converges or diverges. Basically, it comes down to whether or not this area between the curve and the x-axis 2 and infinity, is that area finite? Does it converge? Or is it infinite and it diverges? Certainly, this gets really close to the x-axis really quickly. Look, at x equals 3, I can't even see this function anymore. All right, but enough about the actual graph of this thing. How do you handle stuff like this? Well, one thing you do is you start with replacing this with a letter b. So I'm going to take the limit as b approaches infinity of the integral from 2 to b of e to the negative 5p dp. Okay, well, we can integrate that. There's nothing wrong with that. Now, one thing that I do expect is that you keep around this limit stuff until we're all done with it. So it's going to be limited as b approaches infinity from 2 to b. Now, what's the antiderivative of this going to be? Well, it's going to be e to the negative 5p, but I'm not just integrating e to the x or e to the u. I've got this extra little thing up here. And that's going to give me a constant here in my integral or my antiderivative. Does anyone know what constant I should write out front here?
Negative 1/5.
Beautiful, negative 1/5. I always think of it this way. If I were to differentiate this, I'd end up having to multiply by negative 5 because of the chain rule. Since integration is the opposite operation, instead of multiplying by negative 5, I'll divide by negative 5 or multiply by negative 1/5. Perfect. Thank you. Okay, so let's keep going. If you want, you can pull that negative 1/5 all the way out in front. Negative 1/5 times the limit of 2 to b of e to the negative 5p. And let's plug in our limits. That's going to be e to the negative 5b minus e to the negative 10, right? 5 times 2. Oh, you know, I forgot something. You guys should get down on me. Should be screaming and hollering at me. Wait a minute, Mr. Parent, you made a mistake. What mistake have I made?
Did you
Forgot
forget
my
the
limits. Yeah, there you go. I need to take the limit as b approaches infinity. That should be really right here. So, but I can finally get rid of the limit because I can take the limits. Now maybe it helps you, negative 1/5 limit as b approaches infinity. Instead of writing it as e to the negative 5b, I'll write it as 1 over e to the positive 5b minus 1 over e to the 10th. And now we can work on those limits. Well, the only limit that I have to really figure out is this. As b approaches infinity, what's going to happen to that term? Well, this term's going to get really, 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 really large very quickly. And if I divide 1 by a term that's getting ever larger, where's this quotient going to go?
0.
0.
0. Good. So that goes to 0. And that gives me negative 1/5 times negative 1 over e to the 10. The two negatives cancel, so I'm left with 1 over 5 e to the 10th, which is really a really small number. No idea exactly what it would be, but it's going to be really small. There's just not that much area between the curve and the x-axis between 2 and infinity. But what area there is represented by this. Cool. That was a nice warm-up example. How are we looking on that one?
Can you explain why 1 over e to the 5b is 0 again? Sorry.
It's the limit as b approaches infinity. So if you start putting some numbers here like 10, 100, 1,000, million, a billion, a trillion, etc., this number is going to get really, really huge. And if you divide 1 by some number that's getting really, really huge, it's eventually going to get closer to 0. Imagine you have 1 pizza and you're sharing it with 10 friends, 100 friends, 1,000 friends, million friends. You know, eventually everyone's slice is going to get really, really small. It's going to get close to 0. So that's what's happening here.
Gotcha. Thank you.
Yeah. Thanks for the question. Anything else on the first example here? Okay. Let's try some more. So the nice thing that I can do here is throw in some review of sorts. For instance, this next problem is going to review a little bit of your work with partial fractions. And I'm not sure exactly how much detail you want here. 2 to infinity dx over x times x plus 1, like that. Now, because it's an improper integral, you should start with this limit as b approaches infinity of the integral from 2 to b of dx over x times x plus 1. Now, hopefully by now, you've gone through my video for section 7.5 talking about all the different integration techniques we have. And you can look at this one and say, you know what, that's screaming out for partial fractions. So the question is, how much of the detail of that partial fraction stuff do you want to see? You want me to do it all out? Or do you want to just kind of jump to the happy ending? It's up to you.
Can you do it out?
Sure. So let me kind of do this kind of off to the side here somewhat, or in a sense. So I've got 1 over x times x plus 1. Now I know that I'm going to need an a over this term, and what else? B over that term, right? So that's my partial fraction decomposition. I need to figure out what a and b both are. So the first step that I'll do is I'll take and I'll multiply both sides of this by the lowest common denominator, which is this, x times x plus 1. So that really is going to multiply everything. X times x plus 1, x times x plus 1, x times x plus 1. And when I do that, I get some simplification. This cancels with this. So that's nice. I'm just left with 1 equals. Well, here the x's will cancel, so I'll be left with a times x plus 1 plus b times x. Now, this equation holds true for any value of x. So let's think of some clever values of x that we can choose. For instance, if I was to set x equal to, say, I don't know, -1. Since there's no value of x on the left-hand side, there's no x's there, I just get 1 equals a, -1 plus 1 is 0, plus b times -1, and I end up with b equals -1. All right, so I got b. Now I need to figure out a. What's another clever value of x that I can choose so that I can figure out a this time?
0.
Perfect. Because if I choose a 0, then this term disappears. And what am I left with? I'm left with 1 equals a times 1 plus b times 0. And that tells me that a equals 1. So I've got those two values here. I've got a and b. So let me jump back into this problem then. As the limit as b approaches infinity of 2 to b, this time I'm going to rewrite it as 1 over x minus, because I got a -1 there, minus 1 over x plus 1 dx. Okay, that's fine. Let's keep going. Both of these are terms that we can integrate, right? What's the antiderivative here? Make me look good. Antiderivative here.
ln.
Thank you. So the natural log minus another natural log.
X plus 1.
Yep. And that's between 2 and b. Now, before I start hitting you up with some limits here, let me remind you of something that might be helpful. And that is your rules for logarithms. So there's ln of a times b. There's the ln of a plus the ln of b. And then there's ln of A divided by B, which is the ln of A minus the ln of B. And last but not least, ln of A to the m power is m times the ln of A. Now, similar properties hold true for all different values of the base, not just base E, but I wrote it with base E. I'm going to use the second one, the quotient rule for logarithms, not to be confused with the quotient rule for differentiation. So this becomes a limit as b approaches infinity of the ln of x over x plus 1 between 2 and b. And now let's pop in our limits. So this is going to be the limit as b approaches infinity of the ln of b over b plus 1 minus the ln of 2 over 3. So now we got to get busy thinking about the limit. Let's think about these two right here. As b approaches infinity, what's going to happen to the ratio of b over b plus 1? Where's that ratio going to go?
Maybe infinity over infinity.
Right? But infinity over infinity is not really well defined. Now you could use L'Hopital's rule to figure out the limit here, although I don't think we need to go to quite that extreme. You might notice that the exponents here are the same, right? B to the first power and b to the first power. And in fact, if the exponents are the same, then the limit here, and what I want to do is I want to look inside. So I'm going to look at the ln of the limit. And I can do this because it's a continuous function. ln of the limit of b over b plus 1 minus the ln of 2/3 What's that limit? All right. So you guys should probably do well to watch my video for section 4.4, but you don't need L'Hopital's rule to calculate this limit. Because the leading coefficients, or excuse me, because the degrees are the same, the limit is just the ratio of the leading coefficients. It's going to be 1 over 1. So what I'll end up with is the ln of 1 minus the ln of 2/3. Some help with the ln of 1.
0.
Yay, 0. Thank you. Now, what I'm left with is minus the ln of 2/3. I'm going to stick with that for a second. Now, at first glance, you're like, okay, but let's think about what this problem is asking us, really. Let's see, do I have this one? Yeah, I do. There we go. All right, so let me kind of zoom back out a little bit. There we go. This was from 2 to infinity. So I got to keep on changing these. Sorry about that. That's x greater than 2. Again, we're getting pretty small. My goodness, this is really small. Oh, I put x greater than 20. I wonder why. 2. There we go. I didn't think it was going to be that small. But what we're looking for is the area underneath this curve and the x-axis between 2 and infinity. Now what's going to happen is that if this curve gets close enough to the x-axis fast enough, then this area will be finite. If it is, great, we're happy it converges. So now another thing here. Notice that this area lies above the x-axis. What's that telling you about the answer? What would you expect? What kind of an answer would you expect?
Positive.
Positive. You expect a positive answer. But at first glance, I'm like, well, wait a minute. I got this negative thing. Or is it? Now, one of the things I can do with this is treat this as a -1, and then that negative, by virtue of our power rule for logs, can come up here, -1, and that says really take the reciprocal. My guess is that if you were to do this problem on WebAssign, they would write the answer like this. I would accept this answer. Nothing wrong with minus ln of 2/3. But one thing you should look at and realize is that you should get a positive answer. So what you might want to do is just grab out your calculator and double check that that's actually a positive answer. So ln of 3 divided by 2. Okay, it's a positive answer. And it's not a foolproof double check, but at least it's something. At least you're not giving me an answer that wouldn't make sense in a problem like this. Okay, hey, that was a good one. Kind of a long one, but a good one. And along the way, we reviewed our partial fractions, which is always a good thing. So first thing we did was we split it up, figured out what the partial fraction decomposition was, took the limit of the integral. We can do that by finding the antiderivative. I put these together using our rules for logs. So this is just your quotient rule right here, used in the kind of opposite direction. So we start out with a quotient, we turn it into, or start out with a difference, turn it into a quotient. This part right here, I'm not sure if you guys are a little camera shy. If that's the case, that's fine. But you should be able to calculate this limit. If you're struggling with that, go back and look at the work in section 4.4 with L'Hopital's rule. That'll give you a quick way to figure out that that limit is 1 and the ln of 1 is 0, and the rest is just cleaning it up a little bit. Beautiful. Awesome. Anything else on that one? Okay, let me keep going. Certainly a lot here to do. So our third example. It's going to be this. The integral from, we keep on going from 2 to infinity. Let's just, for giggles, go to from 1 to infinity. Even though I think the original problem was 2 to infinity, of y e to the -3y dy. Somebody help me out with the first step. What should I do first?
I'll change it to b and infinity.
Beautiful. I do want to see you guys writing limits on these things. It's something that I'd probably take off a point for. So just giving you a heads up on that out of fairness. So limit as b approaches infinity of 1 to b of y e to the -3y dy. Okay, that was the easy part. You got yourself a point. But now comes the hard part. You got to earn the other 8 points. How are you going to integrate this?
Wouldn't you use u times v minus the integral of dv?
V to U.
Yeah.
Yes. Integration by parts. Thank you. Absolutely. In fact, because you've got this polynomial term out here, you could actually use the table method. And I saw a couple of you on the last test not using the table method. I don't know. I can do it regularly, or I can use the table method. Any preferences?
Table method.
Table method? All right. Table method's going to work when there's a polynomial here. So if you have a polynomial here, then you can try the table method. We're going to let u equal y. dv is going to be e to the negative 3y dy. We want to differentiate this. And mercifully, it's going to be a short list, right? Derivative here is going to be 1 and then 0. So I only need 2 more iterations of this as well. If I integrate this, I'm going to get e to the negative 3y. And then what? There's a constant here. And boy, I really hope that you get good at figuring out these constants and what I'm going to multiply by, divide by, etc.
Negative
Differentiate.
1/3.
Yeah, so it should be a negative 1/3. And then we do that again of e to the negative 3y. Well, we'll multiply by negative 1/3 again. Negative 1/3 times negative 1/3. What's that give me?
1/9.
1/9. Beautiful. All right. There is one little last trick in doing this with the table method. Do you remember what it is? You got to alternate signs here. It's a plus and a minus. So this times this minus or plus this times this. So let's see what we end up with. We end up with, let's see, here we go. This times this would be negative y over 3 e to the negative 3y. Plus 1 times negative times this would be negative 1 over 9 e to the negative 3y. And all that's between 1 and b. And I still have my limit out front. Trying to think if I want to clean this up a little bit more before I start plugging in limits and trying to evaluate the limit. Yeah, I'm going to take the e to the negative 3y and put that term in the denominator. Limit as b approaches infinity of negative y over 3e to the 3y minus 1 over 9e to the 3y. Between the endpoints of 1 and b.
Wouldn't it be better if you did 2 integrals and then you would be able to factor out the negative 1/3 and the negative 1/9? Or would that not work because we have like
No,
defined?
you could still factor it out here because 1/3 e to the 3y is a common factor for both of those. So I could still factor it out here.
Okay.
I guess I didn't want to deal with a product and a limit at the same time. So I did think of what you're saying. It's a good suggestion. It's just that I think it'd be easier to take a look at the limit of these terms individually rather than having to mess it up with a product. So,
Sure, that
say again?
makes sense.
Okay. All right. Thank you. But I appreciate the thoughts. I really do. Now, let's drop in our limits. This is going to be the limit as b approaches infinity of negative b over 3e to the 3b minus 1 over 9 e to the 3b. Now that's at our upper limit minus at our lower limit, I'll have negative 1 over 3 e to the third minus 1 over 9 e to the third again. And here's where it's helpful to have all that work on L'Hopital's rule behind you so that you can calculate these limits. Well, this one I'm hoping is pretty clear. As b approaches infinity, what's going to happen to this term?
0.
Yeah, that one's going to go to 0 really fast. And even though I've got a b term in the numerator, I've got 3e to the 3b in the denominator, and this is going to approach infinity a lot faster than this. And again, that's going to go to 0. This would be a good one to use L'Hopital's rule with. So L'Hopital's rule says if you have something of the form infinity over infinity when you're taking a limit, that you can take the derivatives and then reevaluate the limit. So maybe if you want, a little star off to the side here, the derivative with respect to b of the numerator is going to be negative 1. B approaches infinity, negative 1. And in the denominator, I'll have 9, because the 3 is going to come out in front, 9e to the 3b. And now this limit clearly goes to 0. So if you wanted to use L'Hopital's rule here, you could. When I distribute this negative, both of these terms here are going to become positive. So it's going to become the limit as b approaches infinity. Actually, no, I don't need that anymore, do I? Because I've already gotten rid of the limit. So let's get rid of u. But it's good that I was thinking about the limits because I do want you to keep around the limits till you're all done with them. That's going to be 1 over 3e to the third minus, is a minus plus 1 over 9e to the third. And I imagine there's just some playing around that I could do to clean that up a little bit. Yeah, I'm just not seeing anything that's particularly fun. If I factor out 1e to the 1 over 3e to the third, that's going to be behind 1 plus 1/3. So this is 4/3 times this. 4/3. And overall, you'd have a 4 over 9e to the third. All right, a little bit farther than I needed to go on that last little bit, but hopefully it didn't disturb you too much. The big thing is to get down to at least here. Notice that no matter what the value of this thing is, it's positive, right? These are all positive terms. And if we look back at the graph, you can see that it's going to lie above the x-axis, and you would expect a positive value for that integral. Beautiful. Nice. Nice, nice, nice. How are we looking on these improper integrals? We're going to do a lot of them. We're going to spend most of our time today on section 7.8, and then a little bit of time on 8.1 and 8.2. But for this one, again, kind of nice because it's reviewing some of our other work. Here we used the table method of integration by parts to try and find this antiderivative. We did. We took our limits. We used L'Hopital's rule here to evaluate that limit. Plugged in our limits and then cleaned it up a little bit. Made it look really, really nice because your professor likes it. All right. I'm kidding a little bit. Please don't worry about getting this stuff. Worry about getting here. I'm not so worried about the cutesy arithmetic at the end. All right, let's keep rolling with some more. Do you guys want to try one? I didn't hear a whole chorus of volunteers. What's that?
Can we do the next one?
Yeah,
Thank
sure.
you.
All right, so you're going to need to start out with a U-substitution. And I'll get you started at least that far. So for your U-substitution, here's the thing. When you've got a 1 over x term, the derivative is going to have an x squared in the denominator. So if I do -1 over x, which of course is just negative x to -1, my du term is going to be a negative times a negative. It's going to be positive 1 over x squared dx. So a couple things you should take care of. One is that the limits, and when you do your substitutions, don't try and change the limits. Don't go from, 1 to infinity anymore, because that's the limits for you. Just write a to b. And then when you're all done finding the antiderivative, go backwards. So this limit as b approaches infinity, and I'm going to hand it over to you. And here we go. So a little bit of a jump up in our steps. So you're going to do our substitutions. The one thing we're not going to do is we're not going to change our limits of integration. Now I'm going to be a little bit lazy and a little informal, and I'm just going to write a to b, even though we're already using b here as our stand-in as the limit approaches infinity. But what I want to do is I want to go back eventually to x's, which is why I'm temporarily putting a to b. All right, so that when I find the antiderivative here and I go back to x, now I can go back to my original limits, which would be 1 to b, not 1 to infinity. I am going to take the time to rearrange this a little bit. Because of that negative, I want to put that term in the denominator. I'm still looking at the limits. The endpoints as being 1 to b. And now I can take the limit, or I can plug it in and then take the limit. So it's going to be the limit as b approaches infinity of 1 over 1 divided by b minus 1 over 1. And there's something that's bothering me about this one. But maybe this is a good teachable moment because I think I've lost a negative someplace along the line. We'll find out. Okay, yeah, maybe not. So what's this limit going to be? Well, we can kind of drill down in this limit a little bit and really focus on the limit here. So let me forget about it here. It's going to be 1 over e to the limit as b approaches infinity of 1 over b. And that's really what's going on, is we're going to say, all right, let's just zoom into here. Minus 1 over e to the first power is just e. What's going to happen here? What's this limit going to be? Someone do me a solid.
0.
Yeah, 1 over e to the 0. And e to the 0 is just 1. So I'll have 1 over 1. Now, since e is bigger than 1, 1 over e is going to be less than 1. So this is going to be greater than 0, which is good. And that's the very least that I would expect for a problem like this. So I expect this to be a positive answer. And that all goes back to looking at the graphs here. So let's take a quick look at the graph. Is that this one? Yes, that's this one. All right, and I want to make that for x greater than 1. So, like our other problems, this lies strictly above the x-axis, and you would expect a positive answer. We got a positive answer, so that's all good. Unfortunately for us, this approaches the x-axis fast enough that the area between the curve and the x-axis is finite, and the integral converges. We actually got an answer as opposed to something that didn't converge, which we'll see later in the second half of this lecture. We'll see a couple examples that don't actually work. For now, how are we looking with this one? Let me go back here. If you got a common denominator, you could write that as e minus 1 over e. Would be a nice, clean way to write your final answer. Okay. Let's take a break here.